Niagara Falls, a breathtaking natural wonder, a raging cascade with over 700,000 gallons of water pouring over every second. For most of us, it's a place to absorb and watch in awe the might of Mother Nature. But if you are John David Munday, a mechanic from Keister Center, Ontario, it's also the place where you want to take a cozy ride in a barrel. And not just once. Dave Munday, in September 1993, became the first person ever to go over the fall twice, a fall that had previously killed 4 people. To back this daredevil streak, you not only need smart engineering of the barrel, you also need a rigorous understanding of the physics of the plunge. How long was he in free fall? With what speed did he hit the water? Was the force of impact life-threatening? How did he ensure that the barrel did not sink? Grab your life vests and your pencils, because we're going to do a deep dive, scribble a few equations, and figure this out.
Welcome to the Scribbled Equation. I am Dr. Ashmeet Singh. I'm a physics professor with a PhD in theoretical physics, and I'm here to show you how physics and math are lurking in every corner of our lives. How wondrous and intriguing our universe is. All this by just scribbling a few equations. If you're new here, I hope you will consider subscribing to my channel by clicking on the bell icon below. If you're back again for more, thank you for being here. It's great to see you again. Alright, back to the scribbling.
Let's set the scene. What people commonly refer to as the Niagara Falls is actually the Horseshoe Falls, the largest of 3 waterfalls in the Niagara, and it accounts for about 90% of the water there. It's a whopping 167 feet, which is about 51 meters, as tall as about a 15-story building. Now, as Dave Munday's barrel went over the falls, he was predominantly freely falling under Earth's gravity, which, if you're not too far from the surface, makes all things fall and change speed at a constant 9.8 meters per second every second, what we lovingly call as the acceleration due to gravity. This acceleration is independent of the mass, shape, and chemical composition of the object. Gravity is the great equalizer, I say. Why is g 9.8 meters per second square around the Earth's surface? That's for another day, another video. So Dave Munday's barrel is freely falling at a constant rate of about 9.8 meters per second every second. It starts off with an initial vertical speed of 0, and from there it's picking up speed at 9.8 meters per second square. So 1 second in, the barrel's speed is going to be 9.8 meters per second. 2 seconds in, it'll be 19.6 meters per second, and so on and so forth. So the speed of the barrel is increasing linearly as a function of time. Now, if the velocity is increasing linearly as a function of time, the distance covered will grow quadratically as a function of time. And that's because velocity is nothing but the rate of change of position as time changes. And for a linear velocity function, the position function will have to be quadratic because its slope will be linear. So we find out that the change in displacement as Dave Munday falls is going to be 1/2 g t squared, a quadratic function in time. Now we know that Dave Munday fell through the height of the Horseshoe Falls, which we found out to be about 51 meters or so. So all we got to do is find out how much time it takes for Dave Munday to fall about 51 meters. We can rearrange this and find out the time taken to be square root twice height of the Niagara Falls divided by acceleration due to gravity on the Earth, And this comes out to be roughly 3.2 seconds. Pretty quick fall indeed. As for his speed, we know it increases at about 9.8 meters per second every second, and then in the 3.2 seconds Dave Munday takes to fall to the water below, his final speed, V final, is going to be about 9.8 meters per second every second times 3.2 seconds, giving us about 31.5 meters per second. To put it in perspective, that's about 113 kilometers per hour, or about 70 miles per hour. That's like going on a fast highway, but this time having a barrel for a car and gravity being the gas pedal. It's amazing to think that regardless of the shape or size or the mass of the barrel, Dave Munday would have taken the same 3.2 seconds to fall to the water below and end up with the same 70 miles per hour speed, accelerating at the same constant 9.8 meters per second square. And given that g is a constant, Dave would have physiologically felt the same when he was 1 second into the fall as he was 3 seconds into the fall. And that's because our bodies are accelerometers. They are able to feel accelerations and not speeds. Psychologically, what he was feeling, now that's a whole other story. But it wasn't just the speed that was impressive, it was the force of impact. Imagine losing all of that 31.5 meters per second to a collision with the water. Now for perspective, automotive crash tests at high speeds often involve impact durations of about 0.1 seconds or so, but they involve much more harder surfaces and less cushioning compared to a barrel hitting the water. While it's incredibly hard to precisely know the duration of impact of Dave Munday's battle with the water, a reasonable estimate is to have it about half a second or so, which I'm going to call as delta t sub c, c for crash, to be about half a second. Now, to be able to estimate how much acceleration Dave Munday underwent during the collision, all we have to do is to find out how much its speed changed in that time interval of the crash, making it the acceleration during the crash. Delta V is the change in velocity during the crash. The barrel hits the water at about 31.5 meters per second and then almost comes to a halt after the collision, giving us delta V to be a final speed of 0 minus an initial speed right before impact to be 31.5 meters per second. And all of this happens in just that half a second, giving us an estimate of the impact acceleration to be about 63 meters per second square, and the minus sign out front just tells me that it's in a direction opposite to where the speed was increasing before. That's enough to make a regular human lose consciousness simply due to the acceleration. How much impact force does this translate to? Here, we turn to Newton's second law. Now we know that Mr. Munday's barrel was purchased from the Canadian Coast Guard and was an old diving bell, which weighed about 300 kgs or so. And let's say Mr. Munday himself weighed about 85 kilograms or so, giving us a total mass of about 385 kgs. Now, Newton's second law tells us that a mass m undergoing an acceleration a will feel a force which is the product of the mass times the acceleration, the famous F equals ma second law of Newton. In this case, we're going to use a sub c, the crash acceleration, to estimate the impact force, which comes out to be about 24,000 newtons that Mr. Munday felt during the impact with the water. Now, to put some perspective on that, this is equivalent to the weight of a small SUV, or the force that you would feel during a car crash at a high speed. If that doesn't mean much to you, It's about 1.5 times the bite force of a saltwater crocodile. Now the barrel must have been lined up with padding to absorb some of the shock. But in his 1993 jump, it is said that Dave Munday was knocked unconscious, though he only suffered minor bruises and cuts. And the force of impact wasn't the last thing he had to worry about. He also had to make sure that the barrel did not sink, but rather it would float to the surface. Enter buoyancy. How much buoyancy force did the barrel feel? Now Archimedes' principle will tell us that the force of buoyancy is equal to the weight of the water displaced by the barrel, thus giving us the buoyancy force to be the mass of the water displaced times acceleration due to gravity, which is the weight of the water displaced. Now I can find this out. I can find the mass of the displaced water by taking the density of water times the volume of the water displaced, which is also the same as the volume of the barrel itself, and then I multiply this mass by g. Now, for this barrel to be able to float, we basically want that the buoyancy force is more than the combined weight of the barrel and Dave Munday inside it. The weight of the barrel and Mr. Munday is the net mass of the barrel plus Mr. Munday times the acceleration due to gravity, which for our estimate of about 385 kilograms, this weight comes out to be around 3,700 newtons, more or less. Let's estimate the buoyancy force now. So the density of water is about 1,000 kilograms per meter cube. What about the volume of the water displaced? Now a spherical diving bell will have a volume of 4/3 pi r cube, where r is the radius of the diving bell, and then I also have my acceleration due to gravity, g, at the end. Now for a typical diving bell, r is about 1 meter or so. Plugging everything back in, what we find is that this buoyancy force comes out to be around 4,100 Newton, which is definitely more than the required 3,700 Newton, making the barrel float. It's quite interesting to think that the mass of the barrel made no difference during the free fall, but made a world of a difference when it came to keeping it afloat. "I'll do it again. It really wasn't much of a big deal," said Munday in this 2011 article at the age of 74. Despite stunts at Niagara Falls being illegal and facing heavy fines and numerous foiled attempts by local authorities, Dave Munday persisted with a blend of bravery, physics, and a touch of madness. His successful attempts have cemented his place in the history of daredevils at Niagara Falls. It is a testament to the incredible things that human beings can achieve with a little bit of knowledge and a lot of courage. See you next time.